All right, let's get right into it. Think about this. Inside your body, right now, there are literally trillions of tiny engines running the entire show. But what if we could, take the wheel? What if we could control them? Well, today, we're going to break down the super clever strategies our medicines use to do exactly that. We're talking about the science of enzyme inhibition.
I mean, seriously, have you ever thought about that? It kind of seems like magic, right? How does one tiny pill navigate all the chaos inside of us to find just one specific target? Well, the answer isn't magic. It's biochemistry. And trust me, it's fascinating. It all kicks off with something called an enzyme.
Okay, so the main character in our story today, it's the enzyme. The best way to think about these guys is like tiny, super specialized workers buzzing around inside your cells. Every single second, they're doing millions of jobs, building stuff up, breaking stuff down, rearranging molecules, all at speeds that are just mind-boggling. Honestly, without them, the chemistry that makes you would just grind to a halt.
But, what happens when one of these little workers goes rogue? Or what if we need to slow one down on purpose, like to lower cholesterol or dial back inflammation? That's when we send in the specialist. That's where inhibitors come in. An inhibitor is basically a molecule that's designed to control an enzyme. And let me tell you, it has some really brilliant ways of getting the job done.
So let's look at strategy number 1. This one is all about good old-fashioned competition. We can call this one the competitive impersonator, because that's exactly what it does. It fools the enzyme into thinking it's the real deal.
So this inhibitor is basically a molecular look-alike. Its shape is so incredibly similar to the enzyme's real target, which we call the substrate, that it can slide right into the enzyme's business end, the part that does all the work. That's called the active site. So it's a direct fight for that one critical spot. Here's the play-by-play. Step 1. The enzyme's active site is open, ready for business. Step 2. Our little impersonator, the inhibitor, sneaks in and parks itself right there. So by step 3, when the real substrate finally shows up to get the job done, well, the parking spot is already taken. The work just can't happen because our enzyme worker is busy with the imposter.
Now the key thing to get here is that because it's a competition, you can actually beat it. If you just flood the system with enough of the real substrate, you can basically overwhelm the inhibitor and win the spot back. This means the enzyme can still reach its absolute top speed, what scientists call Vmax. But, and this is a big but, it now takes way more substrate to even get it started. And this isn't just theory. This is exactly how some of the most common drugs you've heard of work, like statins blocking cholesterol or ACE inhibitors lowering blood pressure.
Okay, but what if you don't want to play fair and compete directly? Well, our next strategy is a little different. It's less about impersonating and more about, clever, indirect sabotage.
This type of inhibitor, the non-competitive one, doesn't even bother with the active site. It's not a lookalike at all. Instead, it finds a totally different spot on the enzyme to bind to. It's called an allosteric site. Think of it like a backdoor. But when it binds there, it's like a saboteur pulling a lever. It causes the entire enzyme to change its shape, and that change messes up the active site, making it way less effective, even if the real substrate still manages to get in.
Let's put it this way. The competitive impersonator is in a race. You can win that race just by adding more of your own runners. But the non-competitive saboteur, it isn't even in the race. It's busy changing the shape of the finish line itself. And it doesn't matter how many runners you add, you can't cross a finish line that's all twisted and warped.
So the impact here is totally different. Since there's no fight for the active site, the substrate can bind just as easily as before. The attraction is the same, but the enzyme's top speed, its Vmax, absolutely plummets. And why is that? It's because a bunch of your enzyme workers have been sabotaged. They're just not working right, which brings down the whole team's productivity. A real-world example of this is how certain molecules can shut down enzymes that are crucial for making glucose in our bodies.
All right, strategy number 3 might just be the sneakiest one of the bunch. This one is all about timing. This inhibitor doesn't go after the enzyme by itself. No, it waits for the perfect moment to spring its trap.
This is the uncompetitive inhibitor. And man, is it patient. It totally ignores the free empty enzyme. It just waits. It waits until the enzyme has found and bound to its real substrate. Only then, once they're already together, does a new binding site magically appear. And that's where the inhibitor swoops in, locking them all together in this useless three-way complex. It's literally a trap, making sure the job never ever gets finished.
And the effect here is, well, it's kind of weird. The top speed, Vmax, definitely goes down. That makes sense, right? You're trapping workers and taking them out of the game. And here's the crazy part, the enzyme's apparent attraction to its substrate actually goes up. So why? Well, because by trapping that enzyme-substrate complex, the inhibitor stops it from falling apart. So from the outside, it looks like they're holding on to each other much tighter. This is a really potent mechanism, and we see it used by nasty poisons like arsenic, but also in important therapies, like how lithium works to treat bipolar disorder.
Okay, so everything we've talked about up to now, the impersonator, the saboteur, the trapper, they've all been reversible. The inhibitor can pop on and it can pop off. But this last strategy, this one's different. This one is for keeps.
Yeah, this is what's often called suicide inhibition. And the name fits, because once an enzyme gets a hold of this kind of inhibitor, there's just no going back. The enzyme is permanently stuck in that form, completely taken out of commission.
It really all comes down to the chemistry. See, the other inhibitors use these relatively weak, temporary connections. But the irreversible inhibitor, it forms a covalent bond, and that is one of the strongest chemical bonds in the book. It's not a temporary handshake, it's a permanent, unbreakable lock. The only way your body can recover is to literally destroy the now useless enzyme and build a brand new one from scratch.
And this incredibly powerful tool can be used for both good and for evil. A lifesaver like aspirin works this way. It forms a covalent bond with COX enzymes, permanently shutting down the signals for pain and inflammation. But on the flip side, a deadly nerve gas like sarin uses the exact same playbook to permanently shut down a critical enzyme in our nervous system. The results are catastrophic.
So there you have it. That's the playbook. 4 totally different strategies, from a simple impersonator to a permanent lock, all designed with one single goal in mind, to control the powerful little engines running our bodies.
And this right here is pretty much the ultimate cheat sheet. You've got your competitive type, which makes the enzyme need more fuel to get going, but doesn't change its top speed. Then non-competitive, which just lowers that top speed, period. Uncompetitive is the weird one. It lowers the top speed and makes the enzyme seem extra clingy to its substrate. And finally, irreversible. Well, it just takes the enzyme out of the game for good.
So what does any of this matter? Because understanding these tiny, microscopic battles is literally the foundation of modern drug design. When scientists are creating a new painkiller, a new cancer drug, or a new antibiotic, what they're really doing is picking the perfect strategy from this playbook to take down a very specific enzyme.
And that kind of leaves us with a final big question, doesn't it? Now that we know the strategies, just imagine the possibilities. What future diseases could we finally tackle by designing the perfect inhibitor, the perfect key to control just one of the body's trillions of tiny engines? That, right there, is the awesome power of biochemistry.